welcome to the lecture 5. Let me do a brief recap of what we did yesterday. That was essentially illustration of the technique of line sweep for the problem of finding pairwise intersection of given line segments, right. So given a set of line segments, we want to find all the pairwise all the intersecting pairs, and we would like to do it in time that is proportional to the actual number of intersection. Okay. The order n square algorithm is rather trivial and straightforward, but it's kind of an overkill for the situation where you have very few intersections, right. So, for that we developed this technique where we do the line sweep, and the line sweep method is so just going back to yesterday's example. So, this red vertical line is a line that we are hypothetically sweeping across this given set of line segments like this, and at any point of time the snapshot is essentially the intersection of the line segments with this vertical line, and we also maintain what is called the sorted intersections, sorted from top to bottom of the line segments with the sweep line. Okay. So, for instance, at this juncture the sorted order is 4, 2, 3, then after the intersection it actually becomes 2, 4, 3 and so on and so forth. Okay. And in this process, as we sweep past all the intersection points, okay, and we can record these events correctly, then essentially we have done our job. Yes.
So, from this, suppose there is one or more line segments which are parallel to the line which are through which we are sweeping. How would we come to know that we are about to encounter and
no. So, I had also made this assumption that let us assume that there is no vertical line, and how we can make the assumption? You can just do a random rotation. I can get away with this. You just take any given set of line segments, not that we can't handle it, but these are very special cases for which I am saying that the easy fix is that you just rotate the coordinate axis by some random amount theta, and that will fix everything.
So, during the whole process we may have to rotate the line many times?
No. There are only n line segments, right, and you have infinite choices of slopes. So, for most of the slopes there will not be any vertical lines. Yeah, so, that's where we are exploiting the fact that we are dealing with a real plane. So, the questions like this will come up once in a while, I know that. So, remember this technique of a random rotation, but there are other we can also directly deal with it in the algorithm, except that I do not want to get into these special cases. So, this is this. So, now how do we record these events? We observed that there are three kinds of event points. One is when a line segment begins, second when a line segment ends, and when we encounter an intersection point. So, at all these events, the else of x, which is the sorted set of the line segments intersecting the sweep line, that undergoes some change. So, our events are exactly those points where the sorted set undergoes a change. Of course, the actual intersection points, okay, will change continuously, because as we move the vertical line, okay, the actual intersection point is going to change. Okay. So, as we move from this from x, so from this line to this sorry, not even that, just an infinitesimal change. Okay. Obviously, the actual intersection points are changing from here, these are becoming these intersection points, but we are actually only bothered about, or we only record where the sorted order is changing. Okay. So, the combinatorial information is what is important to us, it is not the exact point of the intersection. Okay. So, therefore, we only record though events are only meaningful to us where there is a change in this combinatorial information, not the actual value of the intersection points. Okay. This must be understood. All right. So, then we know that therefore, there are only three kinds of event points, okay, new segments, when a segment ends and when there is an intersection point. Now, these two event points are known to us at the time the input is given to us, all the endpoints are known to us, okay, left endpoint and right endpoints. It is the intersection points that we have to determine, and we must determine them before we actually sweep past the intersection point. So, we must determine before we, as we do the sweep, we must detect them before we actually hit the intersection point. And how do you do that? Then we made this observation that before the intersection points of two line segments, okay, they must necessarily become adjacent. Okay. So, this, you can think about it like just before you cross the intersection point, just the infinitesimal before that, and just after you cross the intersection point, these two intersecting pairs must be adjacent. There cannot be anything in between. All right. And this is also again there is some confusion about what happens if there is a situation where there are concurrent line segments, something like this going through a point. Okay, what do I really mean by that? So, one again easy assumption, simple assumption is to avoid these cases, that we assume that this does not happen. But even if this were to happen, we can pretend that these are actually three intersection points. Okay, the two pairs, let us say 1, 2 and 3. So, I can treat them as 1, 2, 2, 3 and 1, 3, all right, and I can order them in any fashion that I want. So, we can handle it either by assuming that they do not exist, or even if they exist, okay, we can actually hypothetically order them and deal with them in some order. Okay. Again, this is not going to be any bottleneck in the algorithm. Right. So, then at any event point we will check. So, what happens at event point? I said the definition of the event point is such that it is exactly those places where the ordering can change. Okay. So, to detect these intersection between Si and Sj, okay, we know that this information must, I mean, if they were not adjacent before, okay, they must have become adjacent after some event point. So, if from if you just that is just an inductive proof that if you are sweeping from the left to the right, okay, starting from a base case like the left endpoint is recorded correctly, and suppose we have recorded all the event points up to a certain juncture correctly, then all the orderings must be correctly maintained at any point of time, and therefore, when you hit the n plus first event point, which could be an intersection point, the two line segments that must intersect, okay, must have become adjacent because of some prior event points, which by induction we have recorded correctly. Okay. That is the proof of correctness of the whole thing. So, how many event points do we encounter? So, we encounter, so total number of event points, okay, where the ordering else of x change, okay, is 2n. There is a 2n endpoints plus, let us call this capital I, number of intersecting pairs. All right. So, these are the total number of event points that we encounter, and I just argued that we identify all the event points correctly. Okay. So, now to analyze the running time of the algorithm, we need to only analyze how much work or how much time is spent for dealing with each event point. Okay. So, let us say number of operations required to record the changes at each point. Okay. So, if we get a bound on this, okay, then we multiply this by the total number of event points and we are done. Okay. So, here is where again we can if we make this simplifying assumption, but I also mentioned that it is not necessary, that is there is no concurrent 3 segments at a given point. The total number of changes that can happen at any event point with this assumption is constant, right. Either some segments, one segment will be inserted. So, 2 adjacency will be affected, or one segment could be deleted. Okay. Again just 2 adjacencies will be replaced by 1 adjacency. Okay. And if there is an intersection, okay, then exactly one adjacency is affected, that is, well, not quite. So, let's so either, so there are three cases I would say, case 1, case 2, case 3. This is new segment. Okay, segment ends, segments intersect. Okay. So, when a new segment comes, then so the situation could have been something like this, this was the situation at the previous event point. A new segment comes in, okay, maybe it is inserted somewhere here. Okay. So, then what happens is that precisely there is one adjacency created between the top red and so the blue segment and the one on top of it, and the blue segment and the red segment below it, right. So, these are the two new adjacencies that are created. Right. If a segment ends, then so you have a situation like this. Let us say this segment ends. So, if this segment ends, okay, then once this drops out, these two become adjacent basically. So, there is only some local information or this is local changes are happening. Right. And if a segment intersect, two segments intersect, clearly they just swap. Okay. If the ordering here and the ordering here, they are just for these two segments they change. Okay. And if when they change, then of course something that was below it and above it. So, there is this change has to be recorded because now instead of these two being adjacent, okay, now sorry, these two become adjacent.
But at that intersection point, at that x length, there may be others also which are intersecting, right?
No, again the assumption is that there won't be any two intersection points on the same vertical line.
There will be no same,
Yeah. Again, if there is one, just rotate the axis, there won't be any. So, exactly. So, for simplifying that analysis, we are making all this assumption. Otherwise, even that is not required. Okay. Right. So, only some constant number of adjacency information is changing at any event point. Right. So, since there is constant number of adjacencies changing, there is not a whole lot of work we need to do to update this information. Okay. But whatever it is, we have to do some updates. Okay. So, what are the updates that are happening? So, the update is happening to essentially update at any event point. Okay. So, there is updates at any event point. Okay. One is there is some change to this L sub x, right. L sub x changes by some constant, additive constant. So, L sub x and L prime of x, there will be some constant number of changes in the adjacencies. Okay. And of course, if we detect the moment something become adjacent, okay, we have to record. Okay. So, the potential intersection point, right. So, for new adjacency pairs, we compute the potential intersections. Okay. Okay. And we must record this in the, there is a queue that we are maintaining for the queue of event points, right, and update. Sorry. Okay. So, L sub x and this event q both are what? Both are some sorted sets, right. L sub x is sorted according in the y direction, okay, and the event q is sorted in the x direction, right, because the event q is telling us which is the next event in increasing x, okay, and L sub x is telling us what is the ordering of the segments when they intersect the vertical line, okay. So, that ordering is in the y axis. So, you see we are dealing with a two dimensional problem. So, we are actually maintaining some kind of information in both dimensions, right. One in the x axis for the order of the events and one on the y axis in the order the segments intersect the sweep line, right. So, what is the standard way of? So, when we have to update this information at any event point, we have to update these, so we need to update these sorted sets. In other words, we need to update some kind of data structures. Right. So, what is the standard data structure for maintaining sorted sets? Yeah. So, you just maintain some kind of dictionary, whether it's an AVL tree or it's a skip list or whatever. So, you basically need a dictionary data structure, right. So, the data structure required. So, use any efficient data structure for storing. This is a dynamic set, right? Dynamic or red black trees, AVL trees, okay, or even something like skip lists, okay, which is essentially implies that order log n per update. Implies order log n operations per event point, implies order n plus number of intersections times log n overall. Any doubts? So, we have succeeded in designing an algorithm which is not a particularly complicated thing, but one if one did not know about these line sweep methods, one could not just come up with it just like that, but after this basic idea, it is not that difficult to come up with this. Analysis is also fairly straightforward, and what you have got is something that is certainly the running time is sensitive to the number of intersections. Okay. So, it is you can write this whole thing also as order n log n plus I log n, just to if I open out these terms, and it turns out that for finding even one intersection, if I ask you this question, tell me if two line out of the given line n line segments, is there even one intersecting pair? Okay. This is a decision problem. Okay. It is also saying this, like if I give you n numbers, okay, and ask you, are there two numbers that have the same value? Okay. So, this is a very basic fundamental question. Okay. So, among n elements, are all of them unique? It is called the element uniqueness problem. So, this element uniqueness problem is a very basic problem, and it is particularly useful for devising or for arguing about lower bounds in particular. Okay. So, this this line segment intersection point problem is a special case of the element uniqueness problem, that given n line segments, is there even one intersection. Okay. So, this problem is known to have a lower bound of something like omega n log n. To find out if there is a duplicate, you essentially need to sort. That is the basic idea. And so, therefore, the first term in our line segment algorithm is unavoidable, the n log n part. Okay. The second term, clearly I is unavoidable, because it must be at least proportional to the total number of intersections. Okay. So, it is only this one term, a slight niggle here basically, that if we did not have this term, then this was an optimal algorithm. Okay. But it turns out that actually improve this algorithm. Of course, that improvement to this optimal bound, that n log n plus I, okay, makes it about 10 times more complicated and practically impossible to implement. It just becomes that much complicated. So, if you are willing to live with that extra log n factor with I, okay, then you have a very practical and elegant algorithm.
I mean, why is element uniqueness? I mean, sorting reduces to. I mean, I don't see immediately. I mean, if the element uniqueness or anything to sorting, why do you have to sort? Sort has a clear.
No. I am not saying that you have to sort for element uniqueness. See,
but you are getting the n log n bound.
no, n log n mod is not. It is not that you get it from sorting. There are techniques by which from which you directly get this n log n bound. All I am saying is that if the natural thing that would come to your mind to find out if all elements are unique is by sorting, and there is a lower bound. It is not by reducing sorting to this, okay, but essentially that there is an independent lower bound with a different kind of an argument, which says there is a n log n lower bound. So, all I am saying is that, so it essentially means that is that you have to sort.
So, I mean, is that very difficult to do? I mean, is it similar to the sorting where you have to consider all the n factorial permutations, and that's why you have to do? Is there a similar? I mean, can you tell the argument, or is there?
Yeah, I will go through the argument when I discuss about models of computation. Okay, it requires what is called it's called, in the least we have to consider what is called a linear decision tree model. Right? In the least we will have to deal with this. See, in sorting we are constraining ourselves to a very special kind of linear decision, that is if xi is less than xj. But yeah, just comparison. Comparison is a special case of a linear decision tree model. But we can't restrict our, since we are in the domain of geometry, we should not restrict ourselves to just that. Okay, so we will.
You are only doing comparison, right?
No, but why would you restrict yourself to only comparisons? So we will actually you can prove the lower bound with a more a more powerful model. Okay. Not only in a linear decision tree model, we will be able to actually prove it in what is called the algebraic decision tree model, where things can take quadratic, you can deal with quadratic equations, things like that. But I do not want to address it right now. You just have to wait maybe to the middle of the semester till I will take it up. So, so in that linear decision tree model, you can prove directly a lower bound of n log n, and all I am saying is that, so then it amounts to saying that you need to sort. If it is n log n, then why not sort? See, lower bounds are extremely sensitive to the model of computation that I often mention this, that even this n log n bound for sorting, okay, is a misleading lower bound. It only holds for comparison model. Okay. The moment you allow things like arithmetic operations, particularly divisions and multiplications, and indirect addressing, that n log n lower bound does not hold. Okay. And your programming language actually supports all these instructions. So, the n log n lower bound is a completely misleading lower bound. Okay. There are actually algorithms that do better than n log n, okay, and those actually use the power of divisions and indirect addressing. Okay, so this was the So, here this basically concludes our discussion on how do you find pairwise intersections in a given set of line segments. Someone could have asked me by now, what are the applications of this problem. So, there are many applications. As we go in the course, we will see that there are many fundamental applications, but one sort of very natural application is that if you have, let us say, two planar maps, okay, which means that I have some map like this, something, some states, countries, whatever, some information that appears in a map, okay, and I have, let us say, another map which looks like this, okay, and for some reason I need to overlay them, okay. So, it means that I'll be doing something like this. So, the moment you need to compute any kind of overlays of this kind of maps, okay, that will amount to computing these intersection points. Okay. So, this can be solved using what we just discussed. Okay. So, if I need to overlay them, essentially I am redefining my faces, the planar map or whatever I have, to the smaller ones. So, these become my faces now. Right. So, and the intersection points actually contribute to the vertices. This is of course a special case where there are somewhat simpler, somewhat simpler algorithms, because we are actually dealing with two different sets of non-intersecting line segments. Okay. So, even this can be exploited to get something simpler, okay. But then I do not want to get into that. This is one of the basic applications that if I can do a line segment intersection, I can solve this overlay point.
Just want to find the number of intersection points, then is there any algorithm like just finding
Yeah,
the number?
so that is a good question. So, what if I am only interested in finding the number of intersections, okay, rather than the intersecting pairs, and this problem of course does not have the lower bound that we are discussing, n log n plus I, because the total number of intersection is only a number between 0 to n square. Okay. So, we can no longer claim that we run this algorithm, okay, and then after we get the intersection pairs we just count them, but then we have already then spent time proportional to the total number of intersecting pairs, which is not necessary. Okay. So, so the counting version, okay, so that is a good question. So, clearly omega I bound does not apply. Okay. So, I'll give you a very special case, and that will also demonstrate that how one can actually solve this problem much faster. Right.
So, I want to ask another related question, like given this set of intersection, whether there is at all one intersection, just I want to say there is some intersection only. Is that should be much simpler than actually?
Yeah. So, if you are only looking at the problem of detecting if there is any intersection, solving the counting version suffices.
Yeah, but counting is even more because you are
could be, but then
it is 0 or not.
no. So, it appears that counting is harder, but it will turn out that we can actually also count very quickly. So, you do not have to. So, you know that just to detect if there is an intersection, I told you the element uniqueness lower bound applies, that is an n log n, and for the counting version, let me go through that and then you will see what I am saying. So, suppose I have is a very special case of counting where I have I want to do the following. I have a vertical slab, okay, and I have line segments it is all cluttered up. So, sometimes actually in geometry this structure is called a hammock structure. It looks like a hammock. So, the line segments do not end or begin within this slab. all line segments completely go through the slab, all right. And now I am interested in this particular problem, the counting version. I want to know how many intersections occur within this vertical slab, okay. Number of this is my slab. So, one way to solve this problem would be to apply our line segment intersection problem algorithm, okay, do the line sweep, report the intersecting pairs, and of course, if I know the intersecting pairs, I know the number of intersections also, right. But this one, okay, can be solved much faster. I do not need to actually report all the intersections, and why should I report all the intersecting pairs? I am not interested in that. So, what did we actually what was the basic observation that we used to develop the previous algorithm? That when there is an intersection, there is a swap in the ordering. Okay. So, can you generalize that observation to this? Right. So, I know, let us say the ordering, if I know the ordering of the line segments here, okay, so let us call this 1, 2, 3, 4, 5, 6, 7, okay, then I can figure out what is the ordering on the other end. Okay, so, this is 3, this is 4, this is 7, this is 2, no, there is some ordering. So, I know the if I know the ordering of the segments on both sides, and how quickly you can find that? Yes, I am saying that all segments go across this vertical slab. There is no segment starting or ending within the vertical slab. So, how do you find this ordering? Just sort, right. I find the intersection points with the left boundary, I find the intersection points the right boundary, and sort the intersection points in the y direction, and I have the ordering, right. So, I know this ordering on both sides. Okay. So, how can I use that to find out the number of intersections?
So, I have to figure out how many
inversions have happened, right. So, do you know how to find inversions? So, it is just a problem that so I could have, suppose I have 4 elements that I want to sort, and it is given to us in this fashion 3, 1, 4, 2. How many inversions are there? Pairwise inversions.
From the sorted thing.
Yeah. So, the actual sorted set is 1, 2, 3, 4. So, this is what is given to you, and I am asking you how many inversions. How can you find it? How quickly can you find it? It can be more than 3. What is the maximum number of inversions? Well, n choose 2, right. The reverse sorted set, every pair is inverted, right. So, are you convinced that the number of inversions will give you the number of intersection points? So, no? If 2 lines are inverted, I mean for any 2 segments are inverted, they must have an intersection in that slab, right. So, that is obvious, but how do you find this number of inversions?
So, could we do by divide and conquer?
Yeah, good. So, this is an exercise for you. Find number of inversions. Forget about line segments, forget about intersections, just given a set of elements, any set of elements, and which can be ordered, find the number of inversions, and you should be able to devise an n-log n algorithm for that. Which means that we can actually solve this problem in n-log n time, which is much faster than actually reporting the intersections. Of course, this is does not solve the general problem. This is only for a vertical slab, because now we have this situation that segments could end or begin within the slab, right. So, we have a more general situation, but this should give you an idea that that problem can also be solved much faster, and in fact that the general problem itself can be solved in N log n time.
Just to apply this vertical slab over there.
Well, it's not straightforward. Let me say that it's not straightforward, but it can be done. Okay, so any more interesting variations of intersection point problems that you can think of?
So going to more dimensional.
More higher dimensions. Okay, great. So what happens in higher dimensions? In higher dimensions, is this problem a relevant problem? First of all, let's think about it. If you are given lines in 3-dimensional space, okay, why would you be interested in how likely is it that they are going to intersect?
Zero, because they are on different.
Yeah. So, if you asked a probability theorist that I have given some lines in space, in 3-dimensional space, the probability of intersection is 0, because the measure of the lines in 3 dimension is 0 actually, right. So, so that is of course, that we are not looking at an average case or something like that.
But
There
you
are
can do it for planes, up planes.
So, so solving the problem for what are called, these are called patches. So, it is not planes. Again, planes will have, you have n planes, 2-dimensional planes in 3 dimension. Of course, every pair is going to intersect in lines. Okay. So, we will talk about these kind of things when we discuss something called arrangements. Okay. So, this is again a very sort of, what should I say, a very basic problem in geometry, that if I give you some, what this, it could be anything, it could be all kinds of, any kind of algebraic varieties, and I want to find out how they interact between themselves, that whole structure, So, segments are on plane. Okay. So, they partition the plane into some faces, it is like a planar graph. Okay. So, that is basically the structure. Okay. If you go to higher dimension, you talk about 2-dimensional planes in 3D. You can go to even higher dimensions, any d-dimensional space, and talk about basically 0-dimension things which are points, 1-dimensional things that are lines, 2-dimensional things that are planes. So, in d dimensions we will be dealing with about d-1 varieties, and they can also may be linear, may not be linear. So, in general this problem is a very messy and very difficult problem, and you do not want to actually handle it, but at least for the linear varieties, that is planes or hyperplanes in higher dimension, people have looked at this problem. Okay, and we will also do some discussion about this, because it turns out that many problems can be tackled by studying arrangements. Okay, the combinatorial structure of the arrangements carries lots of interesting information, because they are geometrically constrained. I cannot just make two planes intersect in more than one place, because they are linear structures, and so this actually imposes the basic geometric constraints, and that can be used to solve many interesting problems. Right? But again, I will postpone this discussion, and we will talk about arrangements at some point in the course. However, I will still go back to the original problem. How about intersecting lines in 3 dimensions? Why do you think you should be interested in that problem? I claim that it is a very interesting, important problem. Although I said something to the contrary, it actually is a very important problem. Can you think about any practical applications of that? Intersection of rays, why would you be interested in intersection of rays? I mean, rays intersect, fine, they let them intersect, Have you done courses in graphics? That is why I think you are talking about rays intersection or ray tracing or something like that. Even if 2 rays intersect, it does not make any difference to at least the way the people solve the graphics problem of visualization. Exactly, very good. So, these days you hear about these collision paths, right. So, aircrafts taking off from airports, it's one of the most important thing is to sort of the ATC control, the air traffic control, is to figure out if there is any potential collision of the of the landing path. And the reason that they have to be very careful, or that it could happen, is that so it's not arbitrary lines in space. You are actually flying out of airport or landing into airport. Okay, so everything is converging into the airport. So the chances of intersection is very high, and moreover, the corridor of intersection is no longer just that 0-dimensional line, but it is actually, so it's considered to be. I think if you come with even with like 10 kilometers of another aircraft or something, that there's some definition that is called a potential collision. Okay, so you are actually talking about something not really 0-dimensional thing, but corridors like this, okay, which is essentially the landing path or the takeoff path of the airports. And they have to actually figure out, that is one of the problems people actually solve. I mean, how well they solve it, I don't know, because there have been instances of collisions, but this is one practical application that if I know that there are these aircrafts landing and taking off, the big airports in the world, they have a few hundred aircrafts landing in about within an hour or less than an hour's time. So this scheduling has to be done very carefully, and at a time sometimes there is more than one airstrip. Okay, so you have to figure this out very carefully.
But sir, isn't that more of a proximity problem? Because if I am going to this line, I am within say 10 kilometers. So in this 10 kilometers of this and this, so if I have some.
Yeah, so I am saying that it is proximity in some sense. It is not 0-dimensional. Okay, it's kind of a corridor. It's like a tube, but then it's a similar kind of a problem where I have to find out whether there is an intersection. Also, it's not just intersection just like that. If they are staggered in time, there is no intersection. So there is another dimension that is coming into the picture. Not just 3 dimensions, but also the dimension of time is important, right? So it is actually a 4-dimensional problem in some sense. So collision detection needs another extra dimension. So even in 2 dimensions, it's actually a 3-dimensional problem, because even if this is one path and this is another path, the 2 cars are going or 2 trains are going, they will intersect, they will collide only if this happens at the same point in space and time, right. Okay, so let me introduce another problem for which line sweep is very fruitfully used. Let me switch to this one, and that is the problem of okay, so let me just introduce the problem first. So especially people who are interested in VLSI layouts, okay, do circuit design. Okay, so what are they doing? Your transistors are nothing but orthogonal rectangles. Right? So you have this is something. This is what is basically fabricated. Something of this kind. So this is meant to be orthogonal. So whenever these 2 rectangles intersect, actually there is some kind of connection, etc. So it really is a very complicated, huge circuit. Okay, millions of transistors, millions of rectangles. Right. So one very difficult problem, and for which there is no real solution. People use heuristics, is that you want to design, you want to pack as many rectangles as possible, but of course under certain constraints you can't bring them closer than something, etc., etc. Okay, so that is a problem that we are not going to we are not discussing right now. But a more basic problem, more simpler looking problem, is that if I give you this some layout, suppose someone has designed this layout, one of the parameters of this layout is to actually measure the area of the union of these rectangles. The union of the rectangles will be a measure of something like how much current the circuit is absorbing and things like that. Okay. So area of the union of rectangles. So how would you, given a set of n rectangles, okay, given a set of n rectangles, possibly intersecting. If they don't intersect, trivial, right? If all my rectangles, now let me switch over to this one. If my rectangles are like this, disjoint, easy case. Sum, just compute the area of the individual rectangles, add them up, done. Right. What are we given as input? We are given as input the description of each rectangle, which means that we are
more than two rectangles can also intersect at
yeah, absolutely. So, once I know the coordinates of the rectangles, I can compute the area and I just sum them up and I am done. Okay. But then that is not what we are interested in. We are looking at things like this, intersection anyway. Any number of rectangles can intersect anywhere. How would you even attempt to solve this problem?
So I will try to determine the intersections of this. I mean, it's like try to use principle of inclusion.
Oh my goodness, that is an inherently exponential thing. Principle of inclusion exclusion is inherently exponential. You know that, right?
Without using much geometry, only using.
No. So geometry also
Intersection I will compute.
geometric objects also have intersections. Okay, but if you rely on inclusion exclusion principle for any problem, any algorithmic problem, any computational problem, you have already sort of you're aiming for something that is not efficient.
The first idea would be find the intersecting areas and then exclude them.
No, the moment you do this exclusion inclusion,
We don't need to do the exclusion. We find any two rectangles that have a intersection.
okay.
And you, after you have done all the addition, you just reduce that intersection from if you have a pair of intersections.
No, so I have suppose these. So here these two rectangles intersect. Suppose this is R1, this is R2. Okay, this is the part they intersect. So what is that you are suggesting?
You find this area.
Yeah, I find the area.
Okay. And then when you in the end when you are adding R1 plus R2.
That is precisely inclusion exclusion. Sometimes so especially when you have three rectangles intersecting, so you must do that alternating sum, right? That's the problem. So that is that expansion is of terms is inherently exponential.
Apply line sweep method and like sweep it and find the area in between event points.
Okay. Very good.
At each screenshot, you'll have to see what are the areas at the screenshot I have.
Okay, very nice. So it's not the area. There's something. So but you have the right idea. So the idea here is that I thought that maybe we'll go through another iteration of development, but here is the solution is been already proposed. So it's based on line sweep, which I said that was the purpose of this example, and it's what is being said that as we sweep, we will have to somehow keep track of the area that we sweep. Okay, that's what is being said, right? I thought you would actually say that using line sweep I can actually compute all the intersections and actually reduce this case to a situation of disjoint rectangles. That can be done, right? Suppose I actually end up computing all the intersection points, okay, then I can actually I can get so this whole thing could look like this so each small thing could be split up, and these I can make it into disjoint rectangles, and then of course I can sum it up. But if I do that, this is doable certainly. If I do that, then I have this problem that my final solution will actually be proportional to the number of intersections, okay, whereas area is just one number, okay, some so many square meters, okay. For that, why do we need to compute all the intersection points? We can compute all the intersection points, reduce this to a case of disjoint rectangles and sum them up, right. But in doing so, you could have ended up computing all intersection points, and there could be a situation where there are just too many intersection points. I can have this kind of thing, a crossbar situation. So there are about n square. N over 2 rectangles this way, n over 2 rectangles this way, and there will be about n square intersections here. Right. So then if you compute those intersections, our solution will be at least n square. Right. I would like to get a better, faster solution, and what is being proposed, just propose that in the line sweep somehow we need to keep track of that. Okay. So let me elaborate on that, or at least what I thought was being proposed. So again we do a line sweep. Okay. So again we take this thing and kind of sweep from left to right. Okay. What are the event points here? The event points would be essentially beginning of a rectangle or end of a rectangle. Here by the way we are dealing with vertical lines also. So here vertical lines is not a problem because everything is orthogonal. Okay. Either the side of the rectangle is parallel to the x axis or the y axis. Okay. So there is no issue about that. So as we sweep across, so suppose my line is somewhere here. Okay. Suppose I move it by some infinitesimal delta x. All right. So if I move by delta x, okay, suppose we are here. Okay. So the question is that when I go move it by delta x, how much area have I swept? Delta x times?
You have to determine the maximum of the rectangles.
No,
Not the maximum.
not maximum. See, there are gaps here. So this line may have lots of gaps, not just one gap, many gaps. But if I know, let me again amplify this. So essentially the gaps could be like, let's look at the intersection of this line with the rectangles. Okay. So it could look like this. Okay. So some area is being swept, okay, by delta x amount. Okay. This plus this plus this plus this plus this. Right. Only if, by the way, there is nothing that begins or ends here. Right. So if we know the total measure of what is being swept across, suppose that is y, okay, then the area swept when we move by delta x is y times delta x, right, and then the area is nothing but summation of this whole thing.
So, but I mean, suppose your thing is this delta x, so this guy had precluded not the whole thing.
No, then we can't apply. So this delta x, I am saying that in this delta x, only if there is no change in these in the intercepts, yeah. Only when there is no change, then it is delta x times y, and I have to sum it over those delta x where there is no change. So it will be some pieces that I have to sum up. Okay. So no change of total intercepts within delta x, then this will work. Okay. So let us stop here today, and we will think about it, how we can do it. This actually requires also solving another interesting problem.